Well, it'll take a minute to finish the loading here. But I did want to, because we're not going to be able to cover everything in it, I just wanted to look at the table of contents in the left panel here that's going to show up in a second, just to show you. Maybe we'll do just some of these things. Managing data, obviously, you know, most of you know that you typically spend 80%, 70 to 80% of your time is just getting the data in, manipulating the data, nothing to do with the analysis, nothing to do with the visualization, nothing to do with the scientific question. It's just handling the different data elements. All right, maybe we'll try to preload them next time. Okay, there we go. So, the first thing is about importing and saving data in common comma separated value files, exporting structures of data, numerical variables, measures of central tendency, and measures of dispersion. And it sets the foundations of visualization of numerical variables, histograms we already saw, categorical variables. This is an important thing, dealing with missing data. We're going to do an example of this. And for some of you, this section may be interesting as well. What happens if you have a design where in the study you have one cohort largely oversampled and another cohort called a minority sample, where you have much fewer observations? What do you do in these kind of situations, okay? Because remember, when the rule of thumb is that if the sample sizes of one of the cohorts is 2 or more times larger than the size of another cohort, you have a very strong potential for a bias introduced by the majority. Why? Well, because once you start computing variances and whatnot, and various other statistics, the sample size does play a role. Variance is supposed to be a sample size invariant measure, right? We all know that. Because in the calculation of the variance, you divide by 1 over the sample size minus 1. However, if you do analysis of variance, for example, the dominant group is not going to add up anything. It's just in the extreme imbalance where one of the sample sizes 3, 4, 5 times as large as the other one. So you have to be careful with this, okay? Depending upon the statistical technique, you may or may not have to do rebalancing, but you got to make sure that the method is handles gracefully these huge differences in sample sizes. All right, so let me quickly scan over. There are examples of, so R comes up with a whole bunch of data sets already preloaded. Here's an example of an iris flower data set where they recorded, they wanted to see if we can develop classification methods. And this data set is almost, not quite 100 years old, it's very, very old. Ronald Fisher, the famous statistician, who analysis of variance came out of, looked at this data set. It has 50 plants of 3 different taxa for which it's recorded the petal width and length, and then the sepal width and length. And you want to see if these are strong enough descriptors of the taxa of the iris flower. And here are the 3 different types. So this data set is provided, as you can see, directly. You don't have to load it in. It just comes in default with data. Now, we also have a whole bunch of case studies here. If you click on this website, the case studies folder has, I don't know, a couple of dozen very interesting health-related studies. Many of them have a neuroimaging component of them, not all of them though. So a huge autism case, there is handwritten letters. The AOS that I told you about, there is data set in here. You know, mental health services, child trauma, quality of life measures, etc., etc. So this is just an example of reading one of the case studies, case 37, that has world drinking water information in it. You know, things like when was it measured, the country that it's measured, the type of residence and whatnot. So this is the very same thing that I did early on. If you call density, what density does is it's a very difficult mathematical operation for a discrete data set. It tries to find an analytical parametric model that describes the distribution of the data set, and it reports for you what is supposed to be a population distribution, but it's sample driven, right? So it's a little bit of an oxymoron, right? For samples we have histograms, period, but in this case you're kind of pretending that the sample is representative of the population, and you want to really see what the population looks like. So it's a very heavy task, and it's done by something called kernel density estimation, and there's a lot of research on that, but R has a beautiful way of doing that very efficiently, as you can see. Remember, what was how many of you have seen the movie Mary Poppins? Remember when she was singing to the kids? When you sing, she says, you begin with do, re, mi, right? When you begin to read, you begin with A, B, C. When you do initial kindergarten, first grade math, they count 1, 2, 3. Well, when you do statistical analysis, you typically begin with center, spread, and shape. You know, these are the first three things that you have to deal with when you do statistical analysis of anything. So the measures of centrality are important, and there is many of them. There is literally uncountably many measures of centrality, believe it or not. The most popular ones are the mean, but then you have a median, right? Well, and then you have a mode, and then you have a geometric mean, and then you have, you know, various other harmonic means. There's all kinds of things. You can define, any one of you can define a measure of centrality. There is truncated means. You know, the universe is huge of measures of centrality. And measures of centrality are important because they provide you with a single word description of a very complex process, namely the distribution of the feature you're looking at. So, the mean is the point of gravitational balance, right? Okay? Median kind of splits the data into 50% above and 50% below it, right? Okay? And mean and median, for what distribution are the mean and median equal? Pardon me? Right. True, true. But there is a more general description. What distributions? These are examples of distributions for which, right, for symmetric distributions, the mean and median coincide. And then the mode is the most frequently occurring observation and whatnot. But remember, if a process is bimodal, imagine a process that kind of looks like this, right? A measure of centrality is completely meaningless. Does everybody understand that? Because the things that are in between here, it's very, very small chance of observing anything. So the point of gravitational balance makes absolutely no sense. So then you got to talk about the modes. And the modes are these humps where the action happens. You know, that's what you're trying to determine, because, you know, the modes kind of tell you where is the process concentrated. So, you know, these are all coded in our very simple things. You know, they can be done very efficiently. Then the second thing after centrality comes dispersion, variability. And for this, you know, you have obviously, we already talked about IQR, the interquartile range. How far apart are the first quartile and the third quartile that include the central 50th% of your observations. That range is an indicator of how dispersed your data is. You also have the min and the max. You also have the, you know, cute, you know, if you have confidence interval for the variables, right? Everybody knows confidence intervals. That's a measure of dispersion. And there's a whole bunch of other ones that you can also compute very easily in R. Range, etc., etc. Here's the IQR, the interquartile range. I've computed it just for one of the variables, 15. So for example, you can do this for each region and find out if these dispersions for the different regions geographically or in terms of the urbanization of the environment are different. Now, the quantile function kind of returns a little bit more information. It tells you for the water, improved water, you know, what's the 0th percentile, 25th percentile, 50th, etc. Box plots, everybody has seen box plots, right? They give you, the median is the thick line, center of measure of centrality. Then you have Q3 and Q1 are the first and the third quartile, and then you have those whiskers, and the whiskers indicate, roughly speaking, the amount of typical variation, and everything that's outside of the whiskers of these box and whiskers plot is a candidate outlier or some kind of a typical observation. Okay, candidate, not necessarily, this is not a test, this is an indication. Okay, histograms, again, you just do hist and then you provide the feature that you want to plot. These are one-dimensional histograms. There is obviously two-dimensional histograms where you do exactly the same thing but on two variables jointly, okay? And then it looks like a heat map, right? The colors indicate the corresponding frequency of what proportion of the observations are within that region in a way. Okay, the skewness, we all know, right, left skewed. Have people seen this rule before for the normal like distribution? If you have a mean of mu within one standard deviation away from the mean, you have about 2/3 of your observations are guaranteed to be 68% to be exact between mu minus one standard deviation and mu plus one standard deviation. If you extend that range to 2 standard deviations, you capture 95% of your observations. And if you go to 3 standard deviations away from the mean, you capture almost all, with the exception of 3 out of 1,000, right? So these criteria you have some kind of a process, you compute the relative proportion of subjects that are within 1, 2, and 3 standard deviations away from the mean. You compare them to these 3 values, and if they are not very, very closely related, your process does not satisfy parametric assumptions. It's not clear what's going on, but it's different. So you got to be careful with linear models, analysis of variance, all the parametric tests. You know, you got to be very careful with some of that. Okay. For categorical data, what you typically do is you generate these tables. So here, for example, is a table of the World Health Organization water quality thing of the regions. And in Africa, it says there were 797 records that were associated with measurements there. In the Americas, North and South, 613. Eastern Mediterranean, etc. So it essentially, the table function tabulates, computes the frequencies for categorical variables and reports them for you. Here is, for example, for the residence area, 3 different types: rural area, urban area, and total. When it comes to exploring relations between variables, let's skip over the cross table. Okay, so this is an important diagrammatic description of how data is typically stored. This is the closest one, the closest representation of a big data foundational model as you can get. The data elements or the features are stored as columns, and keep in mind that some of these columns, and I'll show you some of these, they're called design matrices. Some of these columns can represent a pointer to a file name or some kind of a cloud resource where the actual imaging data lives. Okay? So imagine the first few variables are going to be the clinical variables. Then you have a few pointers to where is the genetics data. Then comes a few points for where is the imaging data. And then some kind of a cognitive tests and whatnot. And then all the subjects are rows in this specific, again, design matrix, if you wish. I'll show you some examples later on. Okay, and this one I believe... Okay, here's an example where, look at this. Population using improved drinking water sources has 32 missing values. Here's the example of where the summary function returns the frequency of how many, and you see they're not very consistent. So some of these regions probably had missing both in both of these features, but some did not. This one has 0 missing.